Hi, I'm Charmee, and I'm going to talk to you about an interesting way of looking at rotational motion. An elegant way to solve complicated rotational motion problems is by linearizing the system using a concept called linear equivalent mass. Let's work through a problem using conservation of energy so you can see what I mean. You have a ball of mass m, moment of inertia I, and radius r rolling down an incline of height h. Friction causes the ball to roll without slipping, but it does no work, so energy is conserved. At the top of the incline, the ball starts from rest, so it only has gravitational potential energy equal to mgh. At the bottom of the incline, it has translational kinetic energy equal to 1/2 mv squared, because it's moving translationally down the incline, and because it's rolling without slipping, it has rotational kinetic energy equal to 1/2 I angular velocity squared. Now let's remember that velocity divided by the radius is equal to angular velocity. So let's substitute v over r in for omega. So mgh equals 1/2 mv squared plus 1/2 moment of inertia v over r squared. Let's rewrite that a bit. So mgh equals 1/2 mv squared plus 1/2 I over r squared v squared. Now let's factor out the v squared. This I over r squared term is the ball's linear equivalent mass. It gives us insight into what the system would look like linearized. It would look like a block of mass m on a frictionless incline, dragging a block of mass I over r squared over a massless pulley on a horizontal frictionless surface. If you analyze the energy of the system when the block is at the top of the incline and the block is at the bottom, you would see that you get the same equation shown here. This concept of linear equivalent mass can be used in a variety of other rotational motion problems too, like this one with the pulley. A block of mass m is connected to a pulley of moment of inertia I and radius r with a massless string. The block drops a height of h from rest. The initial energy is equal to mgh, and the final energy, using linear equivalent mass, is equal to 1/2 m plus I over r squared v squared. This r isn't necessarily the radius of the rotating object. It is the radius used to calculate the torque. So if the string was connected at this little r here, this I over big R squared term would just change into I over little r squared. This way of analyzing the system helps give us a deeper understanding of what's going on in a system with rotational motion and makes rotational motion easier to understand.